Hello and welcome to this video. In this video I will explain how to generate random variables with a known cumulative distribution function from a random variable with a standard uniform distribution. So I wish to generate some x with CDF f, and I want to do this using a u which is uniform 0.1. And to do this, I wish to use the left inverse function, which I define as the left inverse of u equals the infimum of all the possible values from x. So this is the infimum over the sample space of x, where it is true that u is less than or equal to f of x. So if I try to look at a plot here, where I maybe have a CDF looking like this. Okay, then if I have my u, for example here, for example, then I follow this line out here, okay, then I go down, and this will then be my f left inverse of u. Okay, now first of all I want to prove two small results. The first result is that if u is less than or equal to f of x, then it must be true that f left inverse of u is less than or equal to x. And to prove this, let's first look at from left to right. So we assume u is less than or equal to f of x. Well, this means that f left inverse of u, which we just set equal to some x tilde, well then this x tilde is equal to the infimum of x's where this condition holds. So x tilde fulfills this condition and x fulfills this condition, but x tilde was the infimum of all x's, so particularly this x tilde must be less than or equal to x, and this is exactly the right side, so left to right is okay. Now let me just scroll down a bit. Okay, now I want to prove the other way. So I assume that f left inverse of u is less than or equal to x. Okay then. Nothing stops me from taking f on both sides. So I can consider f of f tilde u. This will be less than or equal to f of x, but this this is an x which fulfills this particular condition. So if I take f of this x, so this would be my x tilde from before, if I take f on this, then it must be larger than my u. And then I see that u is less than or equal to f of x, so this way is also alright. Now, this result I need to prove the most significant thing and the whole point of this method, because now I claim that f left inverse of my standard uniform u has the same distribution as x. And to prove this, I want to prove that they have the same CDF, which is enough to determine that they have equivalent, or that they are distributed with the same distribution. So I consider the probability of f left inverse of u being less than or equal to some x. Okay, I just proved that this is the same as u being less than or equal to f of x, but u is a standard uniform distribution, or has a standard uniform distribution. So this is the CDF of u taken in f of x, but since this is between 0 and 1, then this will simply be equal to f of x, and then I'm done, because then we have that the CDF of left inverse of u taken in some x is equal to f of x. So I find that instead of generating x, I can simply generate. So what we now want to do is we generate u from this uniform distribution. Then we wish to use f left inverse on u and set this equal to x. Then x will have distribution f. Okay, let me give you a very short example of this. So let x be exponential with rate lambda. Okay, in this case, the CDF is continuous and strictly. So if f is continuous and strictly increasing, then it is invertible, and f left inverse of u will be equal to the regular inverse of f taken in u. So here we have f of x is equal to, since it's exponentially distributed, it's equal to 1 minus e minus lambda x. Okay, so far so good. Just give myself some more space. Well, then if I set this equal to something, u, then this means that the inverse taken in u, well, I add this over here minus the u, so I will have 1 minus u, then I need to take the logarithm, and then I need to divide by minus lambda. So this will be my inverse. So to generate, I generate my u, and I set x equal to minus the logarithm 1 minus u divided by lambda, or in this case, it can quite quickly be shown that 1 minus u has the same distribution as u. It will be uniform 0, 1. So I could instead use minus log u over lambda. But any of these will work. It's just in this particular case, 1 minus u can be exchanged with u. This can quite easily be shown using the CDFs. But yeah, I don't want to do that. Instead, I want to try to illustrate this in. Okay, so now I have found some code from one of my other videos about the linear congruential generator, which is capable of generating pseudo random variables which are indistinguishable from a standard uniform distribution. So I can use this function to generate my uniforms. So my goal is to generate x from a exponential distribution with rate parameter, let's say 5. I'm sorry if that sound was a bit loud. Okay, so what I want to do is I want to generate my u's. I'll just generate 10,000 using some starting seed for this function. I'll put that to 1, 2, 3. Okay, then I create, then I have to import matplotlib.pyplot as plt. I have to import numpy as np. Then I create my x's, minus np log, and as I said, this is the actual inverse, but I can just as well use this. They have the same distribution. So u divided by 5. And then these x's should be exponential 5 distributed, or at least indistinguishable from an exponential 5 distribution. So one way to see if this is true, it's in no way a proof, but I will just try to illustrate it by creating a plot figure plt hist of x bins equal 50. Then I create a function f of x, which I get to return the PDF. So 5 times np exp of x minus x multiplied by 5. This is just the PDF of our x. And this is just to compare my histogram with the actual curve. Then I create a linspace 0 to 10 to 100 values. Plt plot xx comma f of x. Okay, and then this should be fine. I think x is not defined. No, of course. Okay, I need to divide. Oh, what do you put into this? So plt hist range density. Density must be true. Okay, this should be better. Yeah, so the blue, let me just make this a bit better. Okay, so the blue is my histogram, and the orange line is the expected, or is the PDF. So they should align, which I think they do, if my x's were actually exponential 5. And we can try doing something else. We can try 0.5. Then I think I will need a larger of this. Then I'll just 0.5, 0.5. Okay, something went wrong. Oh, yeah, 0.5. Yeah, so it still fits quite well. I accidentally stopped this too early, so we need to make this go out to 18 or something. Yeah, okay. So you can judge for yourself whether you are happy with this. There are other ways of generating uniforms which are more precise than this, but this is all I wanted to speak about in this video. Feel free to answer questions in the comments below, or generally just to leave a comment if you like. And thank you for watching my video. So goodbye.